Started. Welcome. It is super nice to see everybody today in this beautiful class. Yes, even you. Let's go ahead and talk about what we are doing today on this beautiful Tuesday. I like your sweater. Today it says pick up the handout or handouts on the way in. We don't have any today. We're going to continue with the handouts that we did yesterday. So today we're going to be looking at our notes on interior of the Earth. But before we do that, let's go ahead and look at the capture question. It says, which of the three main layers of the Earth takes up the most matter? We learned this from yesterday when we were working through our model of the Earth. That was a slice of the Earth that we looked at. We measured, we made a scaled model so that the proportions are correct. And then we went ahead and we calculated the percentage of how much space each takes up. So that's what I want you to be thinking about. While you're writing that down, I want you to know that your quiz retakes are going to be Friday during Liberty Time, and also your larger quiz for part 1 of this unit is tomorrow. So that's going to be on everything from the beginning of this unit until now. Somebody said something. What? You are going to be able to, I'm going to allow you to use your notes for that. So let's go ahead and look at what it is that we are doing. I'm going to go ahead and freeze this, and that'll give you an opportunity to take attendance. I'll put 1 minute up on the clock for you so that you can go ahead and get yourself situated, and that will allow me to do what I need to do and for you to do what you need to do. And your time, my dear, starts now. We've got a lot of people going. Is flu going around? I know a couple people have been out because of flu. Last night was so much fun. I know I said I was going to be quiet, sorry. I'll wait. All right, last night was so much fun for me because I was able to be here and I worked with our robotics kids, and then I was able to go and watch some of the wrestling, and I was able to go ahead and see some of the JV squad, the boys JV that was playing last night. So that was a lot of fun. It was fun to see how much stuff was going on in the building last night. Tonight, what's going on in the building? Anything? Yep.
I mean, tech theaters.
Tech theater? Great. That's awesome. So is it like a performance for SLAP yet?
I don't know. I think the performance is going to be happening like the 12th to 15th. I think that's, I don't know, that's when tech week is.
Okay. No performances tonight though.
No, not tonight. Just tech theater coming up.
Awesome. All right, so let's go ahead and look at your question today. It said, which of the three main layers of the Earth takes up the most matter? So if you could please raise your hand and help me out with that. Which of the three main, first of all, what are the three main layers of the Earth? Give me just one.
Crust.
Okay, we've got crust over here, we got mantle over there. Will? Core. So out of those three main layers, which one takes up the most matter?
Cool.
We're going to go Logan in the back.
The core.
The core, and that was really surprising for me to find out that the core, and the core is broken up into what?
2 layers.
2 layers, what are they? Inner and outer layer. I was surprised. I thought that the mantle was going to take up the most matter, but actually it's the core. And tell me about the density of the core compared to all of the other layers. Will?
Way higher.
Way higher. It's the most dense. It's made, we believe it's made mostly of iron and nickel. But we've never been there. We've never been to the core. So how do we really know, what's our evidence to say what the chemical composition of the core is? So today we're going to start to look at that. We're going to start to look at those layers and see if we can figure out why they are what they are, or how we know that they are what they are. Thanks, darling. All right, so then let's go ahead and hop right into that. Just as a recap, I haven't talked actually, Logan, to the other teachers about whether or not we're going to allow notes. So don't not study tonight. Don't count on using your notes for tomorrow's quiz, because I got to be on board with the rest of the teachers. Why are you looking at me like that?
No, I know we had a quiz tomorrow. We just had a quiz, like.
So that was just like a 4-point quiz. This is like we're ending part 1 of this unit, and then we're going to start part 2 of
Wait,
the.
so it's not a big exam, it's just like a quiz.
Oh my god.
It's going to be like a larger quiz, and then what we're going to do at the end of part 1 and part 2, at the end of this unit, we're going to then combine those and have a much larger.
How many points?
exam. Really good question. Is that what you were going to ask too?
No, I said how many questions?
Oh, how many questions? So right now, I've got 10 on there. I think maybe I might have up to 15 questions.
50.
1,
15. Okay.
1. Good question. It'll probably, if it's 15 questions, I'm thinking I just want it to be 15 points. That's a really good question. Okay, so let's go ahead and get our notes, because there are going to be some questions on the notes or out of the notes, and so I want to make sure we are able to get through that. This is going to be directly tied into, can I look at that? Can you take that out so I can look at it? This is from what we did yesterday. Put this on the screen so everyone can see this. Yesterday we created a model of the layers of the earth. And on this side we went chemical composition, and that means what's inside each layer, right? Granite, what's it composed of? Basalt, how much magnesium, how much iron, that's on this side. Over on this side was the physical properties, how these layers interact with each other. So what we're going to do today is we're going to go through these notes, and on these notes we're going to start with going through the chemical composition part of the earth, and then we're going to go to the physical properties section of the earth. So that's how our notes are going to be set up today. Thank you very much. So in order to do that, we are going to be looking at the note sheet that corresponds with your model. So if you could please get this piece of paper out. You picked this up yesterday. If you could please get this piece of paper out, I would greatly appreciate it. This is going to be, and we started it yesterday, chemical composition on one side, physical properties on the other side. So that's going to be what we're going to be looking at today. Thank you very much. Easy on them. What's that? Your mouth, lady, man. Good God.
You talking to me?
Yeah, John, you. All right. Is this too dark? No. Okay, I just want to kind of show this really well. The starter is named the layers of the earth. I think that we just did a really good job of that because we went through the layers of the earth to talk about our daily questions, so I'm going to kind of skip through that. And these are the 3 main layers as a review from yesterday. I know we started this yesterday. We talked about how a scientist that studies what the layers are made of studies the chemical composition, and a group of scientists that study how the layers interact look at their physical properties. All right. So I believe we got to this point. Is that right?
Yeah.
All right. So when we are looking at these notes, you'll notice that I have put some lines here. I will try to tell you what to fill in. But I'm also going to ask you to do maybe some shorthand for yourself. So when you're looking at something like this, these layers are separated based on I would just put, atoms and molecules in the layer. You don't have to write down every single word. It just takes too much time for you as a student. Asa, do you have this paper out in front of you? No, you don't. You have it somewhere in front of you in those layers. Now is it in front of you?
Damn.
All right, so we talked about chemical composition, and when I mean that, I mean the elements. So we're looking at what elements those layers are made of. Can I look to see how far we got yesterday? Just the first one. Okay, so now let's look at the crust. Here we are. So you are going to fill in this part of what I'm asking you to. Crust is the outermost layer. If you don't want to say most, just say outer layer. You see what I'm saying? But do you see where you're filling it in, Asa? Where it says crust, and then there's a line. There you go. So it is the outer layer of the earth. Talk to me about its density if it's the outer layer. Least dense. By the way, speaking of those layers, if you have done your lab write-up and fixed it and you want to hand it in at any time today, this morning, you can go ahead and put that up there and I'll go ahead and grade that for you. Be patient with me though. I didn't get a chance to grade any of them because I had robotics last night, so I'm trying to get through those today. All right, so now we are at that part underneath the crust where it says composed mostly of silica. If you don't want to write a molecule called silica, then don't. You don't need to put this. Just say it's composed mostly of silica, and this has a low density. So you could say silica and then equals low density, if you want to do that. It's composed mostly of silica. Silica has a low density. Which is important, right? Because the crust has is the least dense layer. The silica has a very low density. This is silica. This is oxygen. When you get one silica atom and two oxygen atom, you get what's called silica dioxide. That Di means two. Silica dioxide. Things that will help you when you get to chemistry next year. All right, here's some pictures of the crust. We live on the crust, unless you live in a cave, and then you live in the crust. I guess you could say some people that have those apartments that you kind of like live downstairs, you partially live in the crust if you live, underground somehow. We use the crust a lot for building roads, houses, monuments, bridges. All right, let's look at what our evidence for composition. So that's on your paper. We analyze rocks near or on the surface. So just write down the stuff that's underlined. We analyze rocks near or on the surface. So you don't have to write everything down. I'm just telling you what to write on that one line that says, or rather right here where it says evidence of composition. What do? We analyze rocks near or on the surface. That's how we know what the crust is made of. We look at the chemicals found in those rocks. Now there's two things. I want you to look at granite, and I want you to fill in that it's 72% silica dioxide. Please write that on that little line next to granite. So when we look at the rock of granite, we see that it's 72% silica dioxide. That's a huge number. So that's why we know most of the crust is made of silica and oxygen. And then when we look at obsidian, we see that 72.5% of obsidian is silica dioxide. Let me show you where we are. You good? Yeah. So right here, evidence of composition would be analyzing rocks near or on surface. And then down below here, you're going to fill in those two lines as far as granite is 72% silica dioxide and obsidian is 72.5%. That's our evidence. Now that's easy because we walk on the crust. But how in the heck are we supposed to analyze what the core or what the mantle is? Right? I'm not going to reach down to his mantle and be like, look, my arm is burning off because it's, on fire from magma. Although that'd be really cool to be able to grab some and look at it. Your fingernails? Oh. Ruining your teeth.
I really am.
All right, let's go ahead and go down to the mantle, my dears. We are now on the mantle. What is the mantle? It is thick, hot layer in the middle of the earth. If you don't want to say of the earth, you don't have to because we're studying the earth. You could just say thick, hot layer in the middle or thick, hot middle layer. Don't have to put of the earth. That's just wasting your time, right? We know what we're studying. We're studying the layers of the earth. Now, if we look below, what are the things that are in this layer? We know we've got silica. We know we've got oxygen, just like the crust. But now we have even more of these two others. So the mantle is composed of silica But there's a lot more magnesium and iron in the mantle than there is in the crust. So Asa, do you see where you're writing that? Composed of some silica, but mostly you're going to put more magnesium and iron. And again, if you are lost, you got to put your hand way up in the air so that I can reach over and pull you in, right? Let me help you. So if we look, we can see that magnesium has a higher mass and iron has a much higher mass. And so as we go down in the layers, our mass is increasing as far as what we've got. Good here? All right, let's look at the evidence. How do we know what we know? Evidence of composition. We analyze what's called peridotite xenoliths. Xenolith is just basically this rock that kind of hitches a ride through the mantle, and it gets carried to the crust where we live, and then we can harvest them and look at them. Did I give you peridotite to look at in your lab? I did. That's a rock that came from the mantle. At one point, that was in the mantle deep down where we couldn't get to it. But it hitched a ride through magma coming up to the crust. I'm going to show you what a picture of a xenolith looks like. When I was doing some field study out in Colorado, I was lucky enough to be able to go ahead and see some xenoliths that were embedded inside granite rocks. That was cool. So these are rocks that come from the upper mantle. Hey, what's up, bud? Yeah, peridotite xenoliths, rocks that come from, and then upper mantle. You got it. Yep, absolutely, 100%. Billy, when he comes back, would you mind just letting him look at your paper so he can get caught up on? Thanks, you're a trooper.
Her table.
All right, shh, girl, shut it. Let's go ahead and look at what a xenolith is. These are xenoliths. So this is magma coming up through a crack, right? So you got the mantle and you got this magma coming up and it's going through a crack in the crust. Xenoliths are rocks like peridotite that have a really high melting point, which means they don't melt very easily. It makes them really hard. When I was trying to take these larger rocks and smash them into small pieces so that they would fit into our graduated cylinder, I mean, it's tough for me to go ahead and break those rocks. So chunks break off through the mantle and then they get carried up. All right, these rocks can flow through the mantle like ice in a pitcher of water. So if you picture ice as the xenoliths in the pitcher of water. When the rocks from the mantle hitch a ride to the surface, we can then analyze their composition. And I want to show you an actual picture of a xenolith in situ, meaning in its situation. This is peridotite. And so that's what this rock is, and it's like an actual inclusion. This is basalt lava. And so basalt is part of the continental crust. So what you can do is you can find these inclusions, and if you do, that's really cool. You know that this came from deeper in the earth than we normally can get to. What do you need, darling? No? Spin in your head like a little swivel. All right, so that's what a xenolith looks like when it's like in the wild, so to speak. We can learn a lot about the mantle from looking at that. We can't get to the mantle, but we look at stuff that came from the mantle. All right. So these rocks are formed in the Earth's upper mantle. We've got peridotite. Notice this is on your paper. Look for the word peridotite. This is what you studied in the lab. It's high in magnesium. I want you to write that on that line. High in magnesium. Notice how low the silica content is. So as we get deeper into the layers, the silica content gets less, and then the magnesium content gets more. So the density is getting more and more dense materials as we get into the core, or towards the core. Then we also have eclogite, and I know I'm probably not saying that right. This is less than 50% silica. It's high in magnesium and iron. Here's what I want to tell you about this word. Every time you see a word high or low in notes, I wouldn't write it. What I would do is I would just put an arrow and I would say like that means high. And if you see something that says low, I would just put an arrow like that. Get your own shorthand, right? So that you don't have to write high in magnesium. You can just write an arrow and then magnesium. That's a lot less work for you to do. Develop those little shorthand for you. William, is the entire screen in play here? Great. I'm so glad you're back. Are we good with this?
Yeah.
Good? All right, let's go ahead and move to the core. Boy, that'd be cool if I could actually take you on that field trip. So the core, it's the innermost portion of the earth. Now, do you have to write portion of the earth? No, you can just write innermost. You could write innermost part, but you don't have to write innermost portion of the earth. Ew. Shorthand it. Notice down here, when we're looking at the chemical composition, here we are starting to get more iron and more nickel now. We've never been there, right? So how do we know? So we're going to look at the evidence. So, I'm sorry, not evidence. Evidence suggests that the core is composed mostly of. So down here where it says composed mostly of, you're going to write iron and nickel. Where it says composed mostly of, okay. Composed mostly of, write iron and nickel. Composed mostly of, iron and nickel. I gave you a lot of space for just 2 words. Sorry about that. I took this, and what originally these were was just one blank area over here and one blank area over there. I'm like, wow, could you imagine just having to like write and write and write? Ugh. No, gross. All right, are we good? Iron and nickel, good. No, evidence down here about is going to be something different. Iron and nickel is good. Oh, what the heck? Where'd you find that? Where'd you see that? Shut up. Yeah. So evidence is Earth's magnetic field. Damn, you like reading into the future or something. So evidence is Earth's magnetic field. Magnetic fields are produced by moving electrical charges. This is a computer simulation of what we believe the Earth's magnetic field looks like. So how do we know that the core is mostly iron and nickel? Because the Earth has a magnetic field. Earth's core is believed to be highly conductive molten iron. So this is under number 1, right? Earth's core is believed to be highly conductive molten iron. What's conductive mean? Yeah. Yeah, I can transmit stuff through it. In this case, like charges. We've got our magnetic field. This is like real life Star Wars stuff. It's like these are our shield. It protects us. So that, along with the rotation, meaning the spinning of the Earth, allows the magnetic field to surround the Earth. And this magnetic field is protecting us from what? Solar flares. Or just the everyday, occurrence of like energy coming in from the sun, stripping our atmosphere. And we need our atmosphere. We breathe it. And so without this magnetic field protecting us, that would all get kind of like washed away by the solar energy coming through those photons from the sun. So that's really important. All right, next. The second thing, everybody look down where it says number 2. The composition of meteorites, called chondrites. This is the second piece of evidence that allows us to understand how our Earth, or why our Earth is iron and nickel. If we break a meteorite open, right, if we look at the inside of it, we can tell by looking at what's the inside of a meteorite, we can assume that that's what the inside of our Earth is. And I want to show you that in a minute. Composition of meteorites, called chondrites, tell us there's a lot of iron and nickel in the Earth's core. So again, you're looking for the underlying stuff. How are we doing? I'm going to show you a picture. These are two small meteorites, and they probably came from the core and mantle of the same large asteroid. So these, if we look at the middle of them, we see that even asteroids have a core, and when we analyze it, we see that it's nickel and iron. We are able to see that it has a mantle, and we're able to see that it has a crust. And so we make the assumption that if we can see this in large meteorites, we are then able to go ahead and see what's in the center of our own planet. Okay, can we stop now? That's distracting to me. I can't even tell you. My ADD is all over the place. If we, scientists have found that the composition of meteorites are mostly iron, okay? And so when we look at that, we can assume that our Earth has the same composition. Why? Because those meteorites are made of the same material that our planet is made of. They came from the same disk swirling around the sun. All right, additional evidence. Now we're on number 3. We can also look towards earthquakes. Has anybody ever been a part of an earthquake? Experienced an earthquake? We even have earthquakes sometimes in Iowa. Seismic studies, that means people who study earthquakes, show that earthquake waves change in what's called velocity. That's a fancy word for speed and direction as they move through the earth. So this is evidence that each layer is composed of different materials, and I'll tell you why. Imagine there's an earthquake in San Francisco, California. If the earth was all the same material and it wasn't in different layers with different materials, we would expect one earthquake over here to go all the way through and be found on the other side of the planet. But that is not what we see. If it starts here, it doesn't just go through and come out the other side. We see what happens is the earthquake gets moved. So what happens is whatever this is in here, it's like deflecting and making the earthquake waves change its speed and change its direction. Because of that, those earthquake waves are coming out in different areas, and we're like, wait a minute, what's going on inside the planet that is making something change its direction? It should just go straight through, but it's not. So this is another form of evidence that tells us something's going on inside the earth. There are different layers inside the earth, composed of different materials. All right, that's that side. We're going to move on to the other side, which is physical properties. On the top, could you please write physical over where it says properties? Now we're on the, I'm not very good with my rights and my lefts.
Right.
We're on the right-hand side. So up on the top, may I touch this? Up on the top right here, I want you to write the word physical right on that. Physical properties now we're going to be looking at. Physical properties describes the way a substance looks or interacts with other substances. So we're going to be looking at the examples of lithosphere, asthenosphere, mesosphere, outer core, and inner core. All right, first things first. I need you to write down that these layers are separated based on how they interact with each other. That's the first thing you're going to write. Ethan. How they interact with each other. There's all kinds of like stuff in here. It's not just straight, easy, basic layers. Good? So we're going to look at these five things. Lithosphere, asthenosphere, the mesosphere, the outer core, and the inner core. Let's look at the lithosphere first. Lithosphere, solid outer layer. Don't write of the earth. We know we're talking about the earth. Just say solid outer layer. Litho means rock. So this is like the hard, crunchy part of our planet. When you're talking about the lithosphere, you're talking about the crust, there are two main types. You're going to have your basic continental crust, which is always going to be thicker, and you're going to have your oceanic crust, which is thinner. Now the oceanic crust, even though it's thinner, it's much more dense. than the continental crust. Continental crust is less dense. And so the continental crust is always going to be riding on top of the oceanic crust because density layers. All right, what's it made of? So notice it says made up of Earth's crust and the upper solid part of the mantle. You don't have to write the word Earth. You can just say it's made up of crust and upper solid mantle. You writing any of this down? Did I lose you? You're good? Let's go ahead and look at the asthenosphere, my dears. This is hot, semi-solid layer below the lithosphere. And I want to talk to you in terms of what the asthenosphere is like. This is what's called the weak sphere. So astheno, I think this is going to be next. Yeah, it means weak. This thing moves kind of like plastic. And I don't know if anybody has ever played with silly putty before. Do you know what silly putty is?
Yeah.
Okay, so silly putty is like the asthenosphere. It is a solid, but it can move very slowly, right? It can move. Now, if you move it quickly, it will crack and break easily. But as long as you stretch this thing nice and slowly, it just kind of oozes and moves like a solid, like a liquid. But it's not. It's kind of like a solid material. What's up? Kind of like oobleck. Yes, kind of like oobleck. That's right. Yep. So I'm going to go ahead and put this here, and we will see what happens over time if I can just let this thing hang, and we'll just see what happens. It should stretch out. All right. What is it made of? So made up of Earth's upper mantle. Scientists describe it as plastic-like. It's kind of like that silly putty. It will move and ooze. Made up of upper mantle. This is important because the lithosphere is able to ride on top of this plastic-like layer. Has anybody ever used a boogie board? Okay, so you know you got that board, if you're at the ocean and the waves are coming in and you can throw that board on the water and then it skims across. Think about like the boogie board kind of as the lithosphere and you're sliding on top of that little kind of layer of water. That's how the crustal plates move. Menace. All right. Asthenosphere. Evidence. Don't write anything down here. The heat from volcanic lava comes near the asthenosphere. So that's where the heat from all of that comes from. Write down this important interaction in your notes, please.
What was it made out of?
Okay, let's go back. Made of Earth's upper mantle. So you can just write upper mantle. And then the interaction is the solid lithosphere floats on top of asthenosphere. So they have said solid lithosphere, semi-solid asthenosphere. If you want to put that, you can. If you want to save yourself some even more writing and just say lithosphere floats on top of asthenosphere, that works. But this is going to be critical in our part 2 of this unit when we start talking about plate tectonics, how the crust is moving around. It is floating on top of the asthenosphere, kind of like that boogie board sliding on top of that watery layer. Which I've never been good at that. Good? All right, here's a picture of that. We've got this rigid lithosphere. It's solid. It's got the crust in the upper part of the mantle. And then this is the asthenosphere, so it just kind of slides in, on top of that. Let's look at the mesosphere. This is Earth's middle and lower mantle. This is the mesosphere. That is located under mesosphere. You're gonna write middle and lower mantle. I know I've given you probably too much writing space there. What's it made up of underneath that? It's a fluid semi-solid. So again, it's like that silly putty kind of stuff. Or at this point they say it's like molasses. Does anybody even know what molasses is? I don't think anybody uses it anymore. I just bought some molasses to make some cookies for my dad for Christmas. Yeah, so molasses is like a really thick, it's much thicker than like maple syrup. Yeah.
Do you need help?
Good.
Slow like molasses? Slower than molasses. Yeah. Thanks, Karen. Although, and they also say like hot toothpaste. That sounds gross. All right, let's look at some evidence. Earthquake waves increase their velocity in this layer. So again, the reason we know that there's different layers and we're assuming one of the layers is mesosphere is because we know the different materials that earthquake waves can move through because we do studies on the surface. And so if we look at on the surface what earthquake waves can move through in a laboratory setting, and then when there's an earthquake like in San Francisco, California, we study where it comes out and how long it took for that earthquake to get to where it is on another side of the planet, we can figure out what the inside of the earth looks like. All right, let's go to the outer core, which would be really cool if I could do that. Outer core is Earth's upper core. You can just write the upper core. What's it made of? Liquid, iron, and nickel. So in this case, it is not solid iron. It's liquid down here. Because in the inside of the earth, there is incredible high temperatures. And so it's hot enough to melt iron and nickel and keep it in a liquid state. Imagine what we could do if we were able to harness all that metal, you know, the things that we could build. But if we started dinking around with all of that, then what would happen is we would ruin our magnetic field, right? We got to protect our magnetic field because then the sun can just scorch us. So it's like, all this money and power, no planet to live on. That sounds about right. All right. The liquid metal is responsible for our magnetic field. Please write that in. That liquid metal is responsible for our magnetic field. So we don't want to mess with it. Plus, imagine how much pressure that is under. If we were able to drill down in order to get that, it'd be like popping a zit, right? That's under a lot of pressure. It would just like erupt out. I just can't even imagine what that would look like. Yeah, a huge volcano of like molten metal. Maybe, yeah. Or Yellowstone. Yeah, is that Yellowstone? Yeah, it's overdue to explode. Do you know that?
What?
Does everybody know about the volcano that's happening right now in Indonesia on the Ring of Fire?
Oh, what are you talking about?
No, there's a volcano. There's volcanoes that erupt every single day, y'all. The closest volcano to us is something called Yellowstone National Park. Has anybody ever heard of Yellowstone? So that's a super volcano, and it erupts around every 600,000 years, and it's about 30 to 50,000 years overdue for an eruption. Isn't that exciting? All right, let's look at important interaction. Could you please write down where it says important interaction? Heat from the mesosphere and outer core move the magma upward into the asthenosphere. So there's an incredible amount of heat, y'all, in the core. So this is hot! Exclamation point. Exclamation point. How many of you have ever traveled to a city like Chicago, New York City, and you have visited someone that is maybe on the 3rd or 4th or 5th floor and there's no air conditioning in the summertime? Holy crap. Tell me about the temperature up there. Hot, because heat rises. So in this case, if this is magma and it's super hot down by the core, this magma is going to rise up and away from the core. Now, the farther away from the source of heat, what happens to temperature? It cools down. It's like if you're right next to a campfire, it's hot. But if you move away from the campfire, the temperature drops. That's what happens to the magma. The farther the magma goes away from the heat source, it begins to cool. Now this isn't cool, but it's cooler than the core. And so then this magma begins to cool off and it begins to drop down because its density increases. Where it heats up and then it rises up again. And so what we have then is we've got what is called convection currents. It's this stuff that drives the land above to move either away from each other or towards each other. In this case, Zael, if we look at these as giant like gears, these giant gears are moving in which direction? Opposite, yeah. And so what's going to happen is this land's going to crack open and this land's going to start to move away from each other. Yes?
Isn't that what happens?
Say again, I'm sorry. Just a second. Shh. What, honey? Okay. So what happens is this. The outer core is hot. You've got all of this magma that is moving up to the asthenosphere where it gets near the crust, because the crust is up here, the lithosphere begins to cool off and then it falls down again. Because density differences can be driven by temperature. All right, let's go to the inner core. The inner core is made of solid iron and nickel. Now, this is weird because we just said the outer core is liquid. So why is the inner core solid? Why do you think? Why do you think, Asa? Damn right, pressure. There is so much pressure. Think about the overburden of all the other layers pressing down on that inner core. There is so much pressure holding it together, even though it's hotter, it's the hottest part of our planet, it can't turn to liquid. There's not enough room or movement for those molecules to be moving around, and so it stays a solid state. All right. Density tells us that these heavy elements sank to the center during planet formation. This was a big part of your lab. Please write the word sank right here. Will, I'm worried, man. I lost you like about 10 minutes ago. Sank goes right here. Pressure tells us that the core is so squished together that the iron and nickel are in a solid state of matter all the time. Like that solid state of nickel, that sphere that I gave you for your lab, picture that like the size of the, 1,216, miles in diameter. A big, huge sphere like that, that'd be worth trillions. Yeah, sick is right. Oops, back up. Additional evidence. Again, earthquakes can reveal that we have a layered earth. We've got different earthquake waves that we're going to learn about next unit, but I want to introduce you to them right now. When there's an earthquake, there's what's called a P wave. That's the primary wave. That is the wave that moves the fastest, and it is the first wave to get to you if you live in a city and there's an earthquake that's going to be passing through. It is the least destructive earthquake. And so what people are trying to do is they're trying to use the P wave as an early warning system. Darling, you're not supposed to have that in your ear.
What?
Don't what me. You are a smart individual. So when we're talking about the P wave comes through first, and people are trying to use an early detection system because even if we can get 30 seconds could get a lot of kids out of a building before the S wave comes, which is the secondary wave, and that brings the building down. Because if I have 30 seconds, I can save maybe half of you, right? And just try to get half of you out the building. Whereas if I don't have any warning that it's coming, then maybe we all die. Do you see what I'm saying? So they're trying to detect them. All right, y'all. That is what I have for you today. My recommendation, listen, I need you to study So go home and look at all of the materials. Give me a second. I want you to go home and look at the materials from the beginning, right? Our density stuff, our fossils, our layers. Those are the things that I want you to study tonight that is going to be on the little quiz, little exam, large quiz tomorrow. Study, study, study. Study, study, study. Write it down somewhere. William, will you shut that off for me? What's your question, bud?